All right. Welcome back. This is example 3 from 1 a day 22, and this is for math 365. All right. So we want to set up and solve this mass spring system. What we have is two masses connected together by the spring setup, and we're going to look at the case when F pulling force or driving force is being applied to the system. So right now we're assuming it's at equilibrium, just kind of setting everything up. And then we turn on the switch and the forcing function is applied to the system. And so the first thing we need to do is write out the system of equations, and then we'll go ahead and solve it from there. Okay. All right. So we recall from Newton's second law that the mass of the spring times the acceleration can be written as mass times the second derivative of the position function. And the forces being applied here are Hooke's law. And Hooke's law states that the force is equal to minus the direction times the displacement. So we're going to use these two ideas to really create the system of equations for this system. And so it's really just looking at the free body diagrams of each of these individual masses and thinking about how are they interacting with each other. Okay. So if we consider the first box, this first box here. Okay. So what's happening with it? So if you imagine the force is pulling it this way, okay, what forces are acting on M1 here? If I draw M1 just representing this box. Okay, so I'm going to pull, so it's going to feel the driving force here, okay? But it's not going to feel it directly because first of all, M2 is going to feel that. And so when F gets pulled, M2 is going to be pulled. And so what's going to pull on M1 from the driving force is actually going to be the connection with the spring constant here. Okay, so that's the connection that's happening there. But then as soon as it's pulled, it's going to feel a force in the other direction, which is going to be responsible from the K1 case here. So you have this force pulling it this way, which is going to pull this, but then the spring is going to pull another force in the opposite direction related to. So this is the force pulling it this way. Then this box, the M1 is going to feel the force pulling it that way, and then the spring is going to pull it this way. And then this is also going to feel the returning force from the spring pulling it back that way. Okay, so that is to say that each of the individual forces on M1 is going to give us the result that we have here. So well, I guess I'll write the system here. So for M1, its equation of motion is going to be driven by the minus K1x in terms of the displacement being pulled back from this original force. That's this one here. Okay. And then minus K2, so the second spring constant times uh, its displacement. So, and that's going to be the second force here. Okay, so those are the two forces that are pulling back on it when we pull it to the right to start off the driving force. But again, it's also going to feel that initial tug here from the motion of the second um, mass being pulled. And so that's going to be plus that motion is going to be in the positive direction at K2 Y. Okay. And Y is the motion with respect to the second mass there. All right, so this is going to be the setup then for the first mass. And then if we look at the second mass, uh, how is that motion being affected? Well, it's going to feel the initial force, just like we saw here, but there's not going to be any additional force in that regard because it's just going to be the force being pulled in that direction. So once this gets pulled, okay, it's pulled that direction, then what happens? Well, it's going to start moving, but then it's going to immediately feel a tug backwards with respect to the constant being that string here being stretched. Okay, so it's going to feel that motion, and then it's also going to feel an emotion. An emotion. It may feel an emotion. It may. I don't know if that's funny, but it will feel the motion. Then also, if this one gets pulled and the pulling force, then that's going to move M1. And so that's going to start a motion that way, but then this force result in a pulling force back the other direction. So you're going to see this combination of forces acting on M2 here. And so you get M2, fill that. Its equations of motion are going to be written as K2x minus K2y plus the initial driving force F of t. Okay. We will also assume for our solutions to work for us that x at the starting point, and then the derivative, we'll assume that those are zero. And also, we will assume that those initial conditions, this is the initial conditions, are set for us so that when the timing of the driving force doesn't start until we start the clock. So everything's at rest prior to that situation. That's just going to make it helpful for solving the system momentarily. Okay, all right, let's go ahead and plug in the information that we have given us into our system here and look at then transforming it via the Laplace transforms and solving. Okay, so this becomes applying M1. We get 2x double dot equals negative 6x plus 2y, and we get y double dot is equal to 2x minus 2y plus 40 sine 3t. Okay. Let's compute the Laplace transforms of each of these. So we're converting each of these using the Laplace transform to that entire system. And then if we do that, that guarantees that we get 2s squared x plus 6x. I'm using the capital X and the capital Y to represent the Laplace transform. So this would be the Laplace transform, or in the S space, minus 2y equals 0. And then that looks like x dot. That was just my pen touching pen. So sorry for confusing there. S squared y minus 2x plus 2y minus 120 over s squared plus 9 equals 0. Okay. All right, so there is our system. And now we can solve this system of equations. This is kind of like a linear algebra solving, right? We have a system of equations. We have two equations and two unknowns, capital X and capital Y. So to solve that, we could use Cramer's rule. And in doing that, we would set up the matrices with the d values. And so what does that give us? It gives us that d is equal to s squared plus 3, and then s squared minus plus 2 minus 2. Okay. All right. So that means that d in the x direction is equal to 0, 120 over s squared plus 9, negative 1, and s squared plus 2, which gives us 120 over s squared plus 9. And dy is equal to s squared plus 3, negative 2, 0. And 120 over s squared plus 9. And this determinant gives us 120 s squared plus 3 over s squared plus 9. Okay. Now that we've done that, we can solve for x, and that gives us then that x is equal to, running out of room here, x is going to equal 120 over s squared plus 9 times s squared plus 3 S squared plus 2 minus 2. Okay, and y is equal to 120 s squared plus 3 all over s squared plus 9 s squared plus 3 s squared plus 2 minus 2. All right. And finally, to convert these into solutions or back into our t space, since we're in s space now, we need to take the inverse Laplace transforms of both of these sides. So if I took the inverse Laplace transform of this side and the inverse Laplace transform of that side and the inverse Laplace transform of each of those sides. I did this in maxima, and the results I got for x of t finally then are going to give me 5 sine t minus 4 sine 2t plus sine of 3t. And y of t then is going to give us 10 sine t plus 4 cosine, no, sorry, 4 sine 2t, getting ahead of myself there, 4 sine 2t minus 6 sine 3t. Okay. All right. So then those are with our initial conditions assumed up here, the resulting equations of motion for our connected or coupled uh, system here, two blocks or two masses on springs. Okay, I hope this solution was helpful and kind of shows you the general process. So what did we do? We set up the system of equations. We set up the system of equations based on the force free body diagram, the force. And then from there, we plugged in the given information for each of the masses and spring constants. Then we took the Laplace transform of each side. That created a system of equations with two equations and two unknowns. We used Cramer's rule to simplify or set up this system so that we could solve it. We found D and then complete the square on D, and then we used Cramer's rule to isolate both x and y. Then we use maxima to take the inverse Laplace transform of both sides, giving us our equations of motion for both in terms of position, not equations of motion, but equations of position with respect to the x and y coordinates. Okay, all right. It was a great, fun little example, and I look forward to seeing you in the next video.